Claim number 2 is that the Earth is a sphere with a radius value of 3,959 miles. Supposedly, the Earth is 25,000 miles in circumference, 24,901 to be specific. And the distance from the center of this sphere to the edge is roughly 4,000 miles. It's a very specific size sphere that's supposedly tilted, wobbling, and spinning, flying through space. We can test that claim. Just like we tested the claim of the Earth is moving, we can test the claim of the shape. The globe Earth model makes very specific dimension claims. If these dimensions are falsified, the entire model is falsified. So there's a depiction to show you, of course, what a radius is. Everything uses this R value, this radius value. Gravity, day and night cycle, the distance to the sun and the moon, supposedly how they go to space. They need a radius of orbit. You need a distance from the center to the surface of the Earth and the distance from the surface up to where they supposedly are in orbit to get your radius of orbit. If this value is not true, the entire model is immediately falsified, even distances to places on the Earth, etc. Everything about it. It boils down to this number. If you're actually seeking the truth, you would immediately go and examine this number. The horizon is merely an apparent location. The horizon is defined as where the sky appears to meet the ground. Sky ramps down to the eye level, converging into the horizontal vanishing line, or the horizon, and that's of course where you get the word horizontal from. And then the ground's ramping up to eye level, converging into the horizontal vanishing line. And that vanishing line changes based on atmospheric conditions. So sometimes it's closer, sometimes it's further away because there's more turbulence in the atmosphere, there's more density, there's different temperatures, there's different humidity, there's different obstruction. If the Earth is a sphere with a radius value of 3959, then that horizon is where that arrow meets the surface there. It's going to give you a physical horizon that's curving in all directions always. The horizon moves around. So we don't see an actual physical place or anything. We see an apparent place. The globe would claim, oh, there's an actual physical curve there that's causing the horizon. But since there's an atmosphere, it constantly moves around. You can never see the actual position. And just like you stand at the end of a long hallway or you look down a long street with street lights, you'll see that things above you look like they're converging down. Things below you look like they're converging up. And they look like they converge into each other in the middle vanishing point. The horizon line is not physical. If you see the optical diffraction limit, and this is a mirroring zone here, you see where it looks like the boat is up floating in the air, but no, actually it's just the horizon is just optical, and it makes it look like the boat is actually mirrored here. And you can tell that we have a diffraction limit. We have a limit to how far we can see relative to optical angles and atmospheric conditions. If the Earth is a sphere, this is still true. So we have the definitions of plane surveying here. Below are 5 definitions from various civil engineering forums or textbooks and from Wikipedia, which specify that the Earth's alleged curvature is ignored for surveying projects to 260 square kilometers or approximately 100 square miles, or more specifically to assume the Earth is a flat plane. So if professional civil engineers and surveyors are trained to ignore over 20 meters or 66.6 feet of curvature at 100 square miles, at what point are they trained to factor the Earth's alleged curvature? No, an engineer. Plane surveying is a survey in which the Earth's surface is assumed to be a plane. The curvature of the Earth is ignored. And this is for all engineering, whether building bridges, building railways, building canals. We actually have to assume the Earth's a plane and completely neglect the notion of curvature to do engineering in the real world. We have something called specular reflections, and if you see like the mountains reflected on the body of water here, and we actually have observations from many dozens of miles away where you see really big mountains reflected off the water. If the surface is not flat, you cannot get a specular reflection. If you see here, there's just a little bit of disturbance in the water and you see that the image is being messed up. Now, if this water was actually bending convexly, you wouldn't be able to get a specular reflection. In order to get a specular reflection, the water has to be flat. And this is because if not, you'll have a diffused reflection. It'll scatter. You won't be able to get the actual specular reflection coming from the water, so from whatever the object is to the water to you. Now, light doesn't actually travel, but we perceive it as if it does, and we're not going to digress. The reflection requires a flat surface to then give you a specular reflection. If it is sloping, bending convexly, or if it's concave, you're going to get major distortion. You cannot get an accurate specular reflection. We have long distance specular reflections on the Earth, all over the Earth, and that shows you that the Earth is a plane, that water is flat. If you go to like a circus and you have like the clown mirrors or whatever they're called, the reason they make you look so distorted is because they're curved. And since they're either curved convex or concave, it makes you look crazy. It gives you very distorted proportions. And here is the horizon, which is supposedly Earth curve, and we see just a time lapse of it throughout the day. We see it moves drastically, goes up and down. Now the Earth is not breathing in and out. It's not doing yoga and stretching. Of course, this is just an optical effect because the conditions are changing, and so it's causing the horizon to move around, because that's just the vanishing point, the convergence point, and it's changing based on the different conditions. It's just an apparent effect. It isn't any physical hump blocking things in the distance. Another thing that we have that shows that the Earth is not a globe is long distance laser tests. People will say is, oh, it's actually refracting and bending around the globe, perfectly matching the globe. In reality, what we've done is we've actually gone to the side, we viewed from the outside and showed that it's completely horizontal. Over 30 miles, you can tell that it's parallel with the body of water, completely horizontal. That's impossible. It should be blocked by Earth curvature. They say, oh, it's bending around the Earth curvature. Then how come when we go look at the laser from the outside, we see that it's completely horizontal? They just literally claim that everything's an illusion. Now, here's another problem with the globe Earth. If the Earth is a sphere, then it must be curving down and away from you in all directions. What that means is as you go higher, the Earth is going to be further and further away from you because it's going down and away from you, and you're now going up. Well, here's what actually happens when we go up in altitude on the Earth. You see where the starting line is, you see the horizon, and let's see what happens as we increase altitude. Look at that, the horizon's rising with the drone. The globe would have to claim that its perspective, the horizon, if it's Earth curvature, should be dropping down and away from you. As I go higher above the Earth, it should go further and further down and away from me. But the horizon is rising towards eye level with us. If the Earth's a sphere, this horizon supposedly Earth curvature that's going down and away from my feet. So as I get higher, it should go down away from me further and further. It just converges into that vanishing point. Another problem for the globe is long distance mirror flashes. The military uses these to allow soldiers to communicate and convey their location without other people being able to see it. So you just take a little mirror. If you tip it back and forth, eventually the light from the sun will hit the mirror in just the right way that it will reflect to the observer because it will have a direct line of sight. And the reason that they do this is because enemies can be in the area, but they won't be able to see the guy signaling the mirror flash because you have to have a direct line of sight with the person. You don't see the mirror until the light is at a perfect angle that you can see it. This is an infrared from across a lake where there should be significant curvature blocking this light, but instead we see it. The problem here is you can't claim it's refraction because once you have it curving up from behind a hump or the curvature of the Earth, you're not going to get that direct line of sight at that impact point of the mirror to be able to get the flash. It requires a horizontal line of sight. This has been done far beyond what the globe Earth's math allows. Radio waves can be sent over 10,000 miles with no Earth curvature obstruction. So we can just send these radio waves out horizontally. They can be detected and received over 10,000 miles away. Radio waves are nothing more than non-visible light. So microwaves, radio waves, light, all the same thing, right? In fact, what we typically call light is just visible light. It's all electromagnetic radiation, and there's a huge span of frequencies. And that's what radio waves are. Okay, so you have the radio spectrum labeled there for you, right? As you actually get to 300 gigahertz up to 300 megahertz, that's the microwave range. And then you have that very small portion being the visible light. Electromagnetic radiation going out horizontally can be sent over 10,000 miles successfully and was done in the early 1900s. In 1901, we had the reception of the transatlantic radio signals by Marconi. If you have this tower that's just, a few dozen feet up, and then you shoot a radio wave out, well, the curvature of the Earth is going to block the wave. So you can't send it 2,000 miles if you do the math based on how high you're sending the signal out from horizontally, line of sight. Then the curvature of the Earth will block it at less than 200 miles. They're like, that's not going to work, bro. He's like, well, I'm going to try it anyway. First attempt successful, 2,200 miles away. So shot it like the Earth was flat, line of sight, radio wave was received 2,200 miles away. So they had to come up with an excuse, and that's where Oliver Heaviside came in, and they came up with the idea of the ionosphere. And they claim that the ionosphere is an area of the atmosphere that is ionized. Of course, ionized gas is plasma. There's a certain ionization of the gas at a certain layer in the atmosphere that reflects the radio waves back down. They came up with this to explain how the Earth is in fact a ball, even though the radio wave should have been blocked by the curvature of the Earth. This is where you get the idea of skywave propagation. You see the depiction here. If you send something out horizontally on a globe, what happens is it goes towards space because the Earth is dropping down and away from you. They claim, oh, well, it goes up, hits the ionosphere, bounces back down, then reflects off the ground, goes back up, hits the ionosphere, bounces back down, and it keeps bouncing down, up and down. And it said that radio waves topping out with the frequency of about 30 megahertz bounce off the ionosphere in what is called skywave propagation, depicted to the right. Very high frequency signals with frequencies above about 30 megahertz, quote, usually penetrate the ionosphere and are not returned to Earth's surface, and that's from an official source. This creates what is called a skip zone or a dead zone. So if you see the little triangles there, the area in between is where it couldn't be received. They say that the ionosphere tops out at 40 megahertz. If you have ionization and you send a radio wave, it'll reflect back to you if the radio wave is a lower frequency than the ionization. So say you have some plasma over here and the plasma is 40 megahertz. Well, if you send out a signal that's 40 megahertz or 39, so 40 and under, it'll reflect it back to you. If you send out a frequency that's 41 megahertz, it'll go right through it. So if it's a higher frequency, it penetrates directly through the ionization. And here I have, do microwaves bounce off the atmosphere? While lower frequency radio waves can follow the contours of the Earth and bounce off layers in the atmosphere, microwaves can only travel line of sight, typically limited to 30 to 40 miles on Earth's surface. Under normal ionospheric conditions, 40 megahertz is the highest frequency radio wave that can be reflected from the ionosphere. Well, here is the world record, a list of world record amateur radio transmissions. If you look all the way to the left, this is megahertz, it's the frequency. So we have all these above 106 megahertz. If you look a few columns over to the right, you're gonna have the distance in miles right here. And so we have 1,000 miles, 1,500 miles. We have all the way up to 2,500 miles. There was a 106 megahertz frequency radio wave sent 2,500 miles. Now these should be blocked at a couple hundred miles according to the globe Earth. Well, the problem here is, just like it says here, under normal ionospheric conditions, 40 megahertz is the highest frequency radio wave that can be reflected from the ionosphere. These are over 100 megahertz and happen all the time. This is not a rare occurrence. If the frequency is higher than 40 megahertz, it would penetrate directly through it. And in the globe paradigm, continue on to space. And here we have them, instead of going 200-300 miles maximum, we have them going 2,500 miles. That is direct physical refutation of a claim that the Earth is a sphere. You also have microwaves, and they have a significantly more narrow beam. There's such a higher frequency, they don't span out as much, and thus they have much smaller span of diffraction. We have microwaves depicted as orange and radio waves depicted as the gray one. You'll see you have the microwaves shooting out and then also the radio waves. This hill here is basically going to represent the curve of the Earth. If we send these radio waves out to the hill will block the radio waves because the hill is higher than the tower, right? But since the radio waves are spanning out so much wider, part of the radio waves will actually span out to above the hill, and then it'll go past the hill and then fill back in behind it. And this is called diffraction. The problem is the microwaves don't span out as much, so it can't get past the hill because it's not wide enough to even be diffracted around the hill. Microwaves travel by line of sight. Unlike lower frequency radio waves, they do not diffract around hills, follow the Earth's surface as ground waves, or reflect from the ionosphere. So terrestrial microwave communication links are limited by the visual horizon to about 40 miles. Now we have them much longer than that, and of course the horizon shouldn't just be visual, it should be a physical geometric place, which means we should be able to do the math and know exactly where the physical curve of the Earth is. Doesn't matter where we visually see it. The microwave frequency range lies between 300 megahertz, 300 gigahertz. Beyond 40 megahertz frequency doesn't get reflected back by the ionosphere. It can pass through the ionosphere due to the microwave frequencies are not suitable for ionospheric propagation. Well, here we have them going 50 to 250 miles with a 99.9% success rate of reliability. That's a problem because it can't just be, oh, it just randomly scatters and we get it. Well, no, the signal strength would have to drop down almost completely, which they don't, and you wouldn't have a 99.9% reliability.